orientation of the sample. Because 2 nanometer is very usually to have a pinhole. So if you have a pinhole, you have a short. Then you don't have then you have normal the spin-dependent tunneling. You have only the short current. So it's difficult at the beginning. That's why I think the experimentalists spend so much time to realize this one. Okay, I will try to, and this is standard. So basically, you can see here's antiparallel. You have a higher resistance here. Okay, so it's higher resistance, and go to here. You can apply magnetic field to get the same direction, and then resistance go down. So this is the typical behavior here. Okay, because of time, I will switch to the one of the application, interesting application of the spin-dependent tunneling. You can apply the spin-dependent tunneling in a STM. So you can found a spin-dependent, so let's skip this part. This part is simply you can use also in organic material. You can study the spin polarized electron transport in organic material. All right. Don't have time to this one, but at least I show the photo, the picture of my student. That's very important. Okay. This one is spin-dependent tunneling, the same. But instead of tri-layer, we have a tri-layer in STM. So we have a tip here. And we deposit the ion field. And this is your sample. And where is the insulator? The vacuum here is the insulator. Right? So you have a sphere, you have a spin-dependent tunneling here. Of course, this is not perfect as a tri-layer system. So you can see, so you have a spin. In that way, so your tip, your STM tip become spin sensitive, depending on the relative orientation between the tip and also your sample, the magnetic sample. This is machine. Okay, the machine we built up actually spent also a lot of time. So then you can see this is my former PhD student. He did the first experiment of the spin polarized STM. I think it's in Taiwan. So this technique has been actually about 15 years ago has been found in the Wiesbaden and the Hamburg school. Actually, they have very, very good the spin polarized STM. But okay, because the very sensitive the contrast here. So you can see here the contrast here. So the spin up and spin down. So you can see the contrast here, and you can see here the relation here is even you can see the interference. This is actually is the particle at the surface you where we have it here, and you change also the bias voltage. So you probe the electron at a different binding energy, basically. So then you can see the contrast will be also change because you probe the different spin polarization at the different binding energy. Okay, and sometimes you can also change by changing the binding energy. You can change the spin polarization. You can reverse the binding energy, the spin polarization. In particular, in the organic material, organic material can be also induced some spin polarization by the magnetic material. So quite interesting is my student find a very special tip to get. So we can in situ switch the magnetization of the tip, and you can find at the beginning you can have the black and white. This is represent a different spin orientation, and we switch the spin of the tip. You can switch the contrast here. Just simply you switch the circular polarization with the synchrotron radiation in the synchrotron radiation. Very similar. However, it's difficult. The way is simply you go very close to the sample without crashing the tip. Okay, without crashing the tip. That's difficult. So then I asked him, as he showed me these two experiments, I show, oh, you needed to show me. This did not happen by accident. You needed to go back. So then he tried, I don't know how much time he tried, he go back and he find another way to switch back the spin polarization of the tip. And then you can find go back here. So the 1, 2, 3, so at the same position, you can switch back here. And you may ask me why you need to such techniques to switch the spin contract. Because in organic material, your oxide material, it's very complicated in electronic structure. You need to switch the spin polarization to make sure your contrast is really due to the magnetization instead of the electronic structure. That's why we need to have such a special technique, in particular for the duplicate system here. So I will show this is a organic material here. We can also show the spin contracts and to see the different spin dependent. Shows my doing my with Yuxuan. Okay, I need to finish the SDA part first. So then the next part here is I tell you. So but the new system on which we are working on. So this from giant spin orbital coupling to the spin momentum lock system. And the difference of the spin system here in such material is we don't need the magnetic material. Because the material itself provides you already the spin itself. So because of the very strong spin over the coupling, if you can control the momentum, so basically you can control the spin. So that's why we call this is a spin momentum lock. But not every system can provide you the perfect spin current or the spin current. I think in next week they try to find out a way in a semiconductor, two-dimensional electron gas, to find out a very good spinning current. However, only happen in the low temperature. And such material, the new material here, can provide you spin current. Actually, it's well-defined spin current at a room temperature here. So there's a topological insulator, for example. So you have Dirac point here. So that's Dirac points because you have a linear dispersion of the energy and momentum. So they're just like the massless behavior, the transport behavior here. The energy is equal to Cp. So the energy is proportional to the P only. Of course, the velocity here is not the light speed here. But it's very amazing here. You can find relativistic behavior in the solid state physics here. Another one is spin over the coupling. You can find the spin over the coupling. The energy is splitting. And in a certain layer, you can also find, if you can control the momentum, you can also find the fixed spin here. So if you apply the electric field, for example, so then you can find the imbalance of the spin up and spin down. So, and you can find actually in the current, you can also find a certain spin polarization if you can apply a certain current into the one direction. So both of material have the certain probability. We are working on right now for doing some spin-dependent transport. But in the following, I will just show you some SDM, pure SDM, spin polarized measurement on such material here. So this also show you here. And this work has been done by the Christoph Butler, also when he was doing the PhD work here. He has a very good Chinese name, Yang Yu. Okay, I don't know how come to the Yang, so he must be here. I never asked him. Okay, so he developed a kind of the XMCD. So the X means a cross-section. That's because that is very difficult to perform the STM on such material. So such material usually will be performed in situ. So you have outside and different material. And usually the surface is very dirty. And if you like to get a good surface, you need to have some in situ cleavage. I will show you this one. So he developed a technique to cleave the surface, basically, to actually explore the surface in situ. So you can get the layer, because this such system is a layer structure. So you can get a beautiful surface here, beautiful you can see. And in this system, the BITEI, on which we are working on, so basically you have the polarization because of different termination. You have the minus and the positive electric polarization. And that's why you have at the interface, at the surface, you have the surface band bending. Okay? As long as you have the surface band bending, you have the electron hole here, and you have the electron, two-dimensional electron gas here. In this way, you can provide two different surface here that provide you different gas, 2D E and two-dimensional hole gas. And this work by such technique to get a good surface, so we can really close boundary between the two termination. You can see microscopic is a very beautiful microscope. STS, you can see the band structure here, so a kind and representing a behavior, typical behavior of the p-n junction. So here is around the 4.5 nanometer. You can see the picture here. That is the one work that has been done. The first time has demonstrated to really indicate a two-dimension p-n junction in such material, which actually is predicted. The second material, second interesting experiment is, we can consider the Fermi surface is a lot of the quasi-particle. And a quasi-particle is basically you can consider as a wave. As a wave, you can be scattered at the impurity and can have formed a certain interference pattern. So, and you can see a lot of different interference pattern here. You can see, just like a drawing. So here, at a different energy, because at different energy you have a different wavelengths due to the different energy. So then you have a different wave pattern here. And what's important is you can transfer this one in Fourier transfer in the two so-called quasi-particle interference. We can find the K-space behavior. However, this K-space is a so-called the Q-space. I will show you later. This one. So this is band structure here. So the scattering only happened from this band to this band. Proposed. Okay? So basically, this we call this as Q, and this is K, for example. And that means we can find the Q span as function of the energy as function of the Q here. So representing the interference, the wave vector here. So you can get the information of the band structure here, and in microscopic here. So you can find also with the SPS in the microscopy, you can find the average effect. But here you can go into the any place to get the local information to know the material itself. I think I will almost finish it here. So you can see you can see the main energy here. So you can change the binding energy. So you can go to the different energy, and you can see here the the interference pattern change also. On the other hand, in the Fourier transform, we can see also this represents you a certain kind of connection to the band structure. Okay, it's not band structure itself, it's a K-space. Now it's Q vector here, so, and I show you here. So I think I need to stop here. So sorry, so we need to stop here. So basically, he developed a new method by simple organic material can protect the topological insulator surface. Here, for example, the iron film is you can find a shift of the topological at the Dirac point here. However, after capping organic monolayer here, so basically you can still keep the Dirac point at the same point. And this is very important for a device qualification by using the topological insulator. Otherwise, you can destroy the topological insulator if you put some electrode to make a contact here. So here you can also see very beautiful Dirac point here. You deposit, he deposit a lot of the iron here, but still, even direct measurement on the iron film, iron island, you can still get a very good Dirac point. I think we have the explanation, but I will skip right now. So I would like to thank my student and also my funding and my cooperator, and so on, particularly the material from the Zhou Hangzhen. Okay, thank you.
So it's a very nice talk, and let me ask the first question. How do you deposit that? Because I'm interested in this topological insulators thing.
We got a sample from the Zhou Hangzhen. And then we also the same way. We use the same way to
create it in
the create in situ.
Oh.
Okay, that's what I like to do also with your sample.
Okay.
So otherwise you will get a very dirty surface, and usually it was a problem actually in the past. Yeah.
Any question? Yeah.
Finally, Unless we know the Moore's law in a transistor, below 5 nanometer, there is a limitation. But your talk, the magnetic density, does it have a limitation? Physics will tell you it's maybe 20 Tesla, 20 T is a limitation also say that. Do you have any feeling?
I think there should be a limitation of the super paramagnetism. If the system is too small, then the Curie temperature will become small. So it's a finite size effect. Then of course you cannot work at the room temperature. You need to work in liquid hydrogen. Yeah. So that indeed is theoretically in principle you have always have some limitation. However, if you use a different function, of course, you can have a different limitation.
Thank you.
So in terms of the devices, what's the typical time scale that you can, how fast is the response?
How fast is about nanosecond. So that the advantage, one of the advantage of the Spintronics is the speed, actually, as compared to the DRAM. Of course, the SRAM is also very fast. Oh, I needed to claim. I need to claim. We are not intending to replace the semiconductor. So don't be defensive or offensive. I don't.
I don't have a problem with that. I've been hearing, this magnetism will ultimately be the semiconductor, and there's talk about what MRAM, right? And now this is nowadays a spin transfer talk.
Yeah.
Right, RAM.
Yeah.
Okay, but still, okay, memory device is still a very small part of the whole IC or technology, ICT industry, and it's hard to beat silicon. I know that because I work on gallium nitride. People has been talking that gallium nitride will replace silicon. It never happened. It's difficult, yeah. But it will be very, it will be very, very interesting to see that if it really happened. It will be very exciting, right?
Let me comment on that. I think two comments. One is on the particular silicon part, because the 3.5 or germanium part, the speed-wise is certainly going to exceed that, and they already the Intel and company already has spent 10 years there. Any time will come. But the important thing is the power consumption, because at the when you drive the VDD from 1 volt to 0.7 to 0.5 volt, the electron in silicon just cannot move. Okay, so remember that that will happen. Okay. Second is on the Spintronics part. Right now, since recently, the people that including Intel that already think beyond CMOS. Okay, so Spintronics has been studied very seriously. Again, that is from the energy consumption point of view. Okay, I think that to replace silicon, nobody ever claimed that. But remember that on the IC part, the digital high-speed part is only like 10%. So that right now is one grow the 3.5 or Spintronics part. In those critical part, it's not 100%. It's only to do 100%. And more importantly, it's not replace the whole silicon. It's a silicon as a platform. And then you have 3.5 or germanium integrate onto silicon. And also remember when you got to look beyond, because in particular for the gentlemen or gentlewomen just standing here, that in 25 years, right now we know the CMOS is going to end. Okay, so one has to look beyond that. And certainly Spintronics is one of very important part. One has to look at very seriously.
Thanks for the promotion.
Yeah, it's definitely. We hope that we can find something else to replace or to improve the performance of the silicon device in the future. No.
I make a short comment on the spin. I think this is an advantage of for the student from the physics department. Spin actually is easy, but on the other hand, it's also very complicated, right? So the spin is there, it's rotation, but it's not only that. So that's the part I'd like to show you today. It's very complicated. Also played a very important role in transport. And for the most of the people on the other side, I mean the engineering faculty, sorry. So they have no good training in quantum mechanics and quantum. Okay, the right question. So, sorry. So basically, you have a certain field, you have a certain background as a physics student. So to play around. That he is also, I think Professor Huang is also the actor of the spin. So I would say it's not only for the application, but also for the new physics in the future, even for the semiconductor-based all electric spintronics. So it's not metal, it's new material, and topological insulators and different new things. They need to have some knowledge of the spin.
Okay, if there's no further question, let's thank our speaker again.